Hi again. I'm still in section 2C. Last video got too long. Uh, I was working hint 4, and it was basically I was supposed to solve a simpler problem, and I just started solving the regular problem right away. That's the thing in real life. You don't know when to use a technique and when not. So I just know that I was working it, and I'm like, boy, this seems pretty hard. I wish I would have, worked maybe a simpler problem to start. I was feeling confident that I was going to get it, but at the same time, I was still unsure. So I'm going to use a different approach. So I'll explain the problem. Basically, you got some coffee in a cup, and I assumed that there was 1 cup of coffee in it, 1 cup. And I know in 1 cup there's 8 tablespoons. No, there's not 8 tablespoons. There's 8 tablespoons per half cup because I actually like cooking and I look at a stick of butter, and a stick of butter is a half a cup and there's 8 tablespoons. Therefore, there's 16 tablespoons in a cup. But I also cook and there's 3 teaspoons in 1 tablespoon. So, bottom line, I got 48 teaspoons of coffee. Now that's assuming that this cup is actually holding 8 ounces. They didn't really say. And then you got another cup. It's got milk. I'm from Wisconsin. I grew up on milk. I grew up on a dairy farm. And there's a cup in there, so there's 48 teaspoons. And what they want to know is if you put a teaspoon of milk in your coffee, turning this into a mixture with 49 teaspoons, 48 with coffee, and 1 with milk. If you mix it up and then you take another teaspoon and bring it back, are the ratios of milk to coffee just flipped, or is one different than the other? It's kind of hard to explain, but I think right here, and when I was trying to solve the problem just straight up, 48 parts coffee, 1 part milk, and you take a teaspoon of that and you put it back in here, and you know that there were 47, and now there's 48 teaspoons in each. Is the number of parts of milk the same as the number of parts of coffee, and vice versa? And that's what we're trying to figure out. The reason this problem's so hard is because you got like 48 things and 49 things, and it's making it a little difficult. So what we're going to do is we're going to make it way simpler. What do you say we go with 10? That wouldn't be a good way to draw 10. So, and we don't have to draw a pyramid, but that could be like the milk, and this could be like the coffee. Why did I do that? So 10's a good number because 10 gives me a really good ratio and percentages that I personally can understand. So what we're going to do is we're going to physically, and we might have to be careful, we might have to move 2 balls over because I did it with 1 and I got a little confuzzled. So let's just take 2 of these and put them over here. So what we have is we have 8 left 2, 3, 4, 5, 6, 7, 8. And then we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, right now, we know we got 8 here and 12 here. We got 10 out of 12 to be coffee and 2 out of 12 to be milk. Now, we're going to have a mixture, and we're going to bring 2 back because it's a mixture, and we're going to be left with, well, 1, 2, 3, 4, 5, 6, 7, 8. But this new one coming back and a black one leaves me with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9 milk, 1 coffee, 9 coffee, 1 milk. The ratios are the same. Well, I don't know if that's gonna truly help me, but it's sure a lot better way to start. I'm thinking the ratios are going to be the same. Now, when I was working it straight up, trying to solve the whole problem, what I realized is this teaspoon coming back had 48 out of 49 parts milk. So 48 divided by 49, which is 0.979 of a teaspoon is toffee on the way back, and 1/49th point 1/49th point 0.02, let's round it, 1, and that was milk. So we're going to add this to the 47 teaspoons of milk. So when you bring it back, there'll be 47.021 parts milk, and it'll be 0.979 parts coffee. And the two add to 48. So we know this mixture over here is 0.979 coffee, and this is 0.021 milk, because those are the ratios. Now this is 47.021 out of 48. So 47.021 divided by 48 is 9.97 or 97%.9 milk and it's 0.979 divided by 48. It's 0.021 coffee, and the ratios are the same. Did I do a good job of explaining that? I don't know. I think I could now, but not a trivial problem. I did solve a simpler problem. It did make me more confident in my strategy that I used. So I guess between the two, I got the answer, and I'm confident that the ratios are the same. Maybe I could have done better, but I don't think that's the point here. The point is to solve problems. And I just solved one using a technique that I've used over the years, and I guess I kind of feel okay about it. Kind of wish I wasn't teaching. I kind of wish I was just like doing problems. Maybe I'd feel a little better. Hint 5. Consider equivalent problems. With simpler answers. So basically, alter the problem so you can get nice answers, and then realize how you work the problem and repeat it for one where you get crappy answers. Let's try. One is decorating a party room that has 10 large cylindrical posts. So you got these cylindrical posts all over the place. I don't know why you have cylindrical posts in a party room. I guess we could go sideways with that, so let's not, use too much imagination. I got 6 posts. One that has 10 cylindrical posts. I hope they tell us what we're doing with them. But anyway, right now, I'm just drawing posts. That's all I'm trying to do. Cylindrical posts. The posts are 8 feet high and have a circumference of 6 feet. These are big posts. 8 feet high, and their circumference, the circumference, let me fix that. The distance around is 6 feet. Hopefully these are blow-ups. These are really big. His plan is to wrap 8 turns of ribbon around each post from the bottom to the top. So he wants to go 1, 2, 3, 4, 5, 6, 7, 8 things of ribbon from the bottom to the top. That'll look really nice. How much ribbon does Juan need? Okay, now we're getting somewhere. So everybody knows that he went around 8 times. So 48 feet for sure, right? But he was stretching it 8 feet. So I'm thinking I'm thinking it's less than, I'm gonna have to draw this. So everybody, I know he went around 8 times. Let me read this right. He went around 8 times. And we know the circumference is 6 feet. So for sure, 48 feet's going to do it. But he's going to have to go up the pole 8 feet. Huh. That's a pretty cool problem. I think it's actually less than 56 feet. What I want to do is look at this ribbon. So what I want to do is, you see this ribbon is going up this pole, and I'm looking at it like this. And I'm kind of seeing triangles. So I'm kind of thinking Pythagorean theorem. But it's a little different than that. If I would cut, let's say they're paper posts and you could actually cut them, made out of cardboard, and then opened up, it literally makes a sheet of paper. And then the lines would look like this, and then they would come straight across, and it would take off again and look like this, dot, dot, dot. This is 6 feet, because that's the circumference, and this is 8 feet. And there's going to be 1, 2, dot, dot, dot. So these are going to be 1 foot high. So right here is actually the length of the ribbon. So we got to find this mystery length. And the question mark length is the square root of 6 squared plus 1 squared. It's the square root of 37. Pythagorean theorem. Sorry, I went pretty quick. So 1 squared plus 6 squared equals question mark squared. Question mark squared equals 37. Square root of 37. So we have 1, 2, 3, 4, 5, 6, 7, 8. So the ribbon is 8 square root of 37 long, which is actually 48.8 feet. So what did I do? The hint of the day is consider equivalent problems with simpler solutions. I almost would want to argue with them. I would say draw the picture, and then I saw the diagonals kind of reminded me of basically a trick I've used a lot in math, is you just cut it and you open it up, and then I actually got a good look at the ribbon. And by working and finding the length of one ribbon, maybe that's what they're talking about, I just turned around and then multiplied by 8 and found the total length of ribbon. Personally, I think it's a combination of experience with wrapping post myself. I'm old and taught math a long time, and I know when somebody gives you a cylinder, a common trick is to open it up, see what it looks like. And then the old Pythagorean theorem actually helped out. So, gotta love the Pythagorean theorem. Not that we've actually talked about and covered it, I just assume the book must think you know that stuff. All right, let's try hint 6. Approximations can be useful. Just like I did last problem. I was pretty sure the answer was under 56. And I knew it was a combination of, you know, the wrapping it around plus at least 8 feet. So, you know, that was, you know, I just kind of approximated, got myself in the ballpark. Imagine a 1 mile long bar of metal, such as a railroad track. I can do that. 1 mile railroad track, just the metal portion, 1 mile. Is anchored, pounded into the ground, is anchored at both ends. And that on a hot day, the length expands by 1 foot. So initially it's 5280. And then we know the length expands at 1 foot, because we live a mile high, 5280. So we know the metal is actually 5283. At 1 foot, 81. But it causes it to bow, of course, because it's anchored at both ends. Exaggeration, big time. And it says it's causing it to bow vertically, so literally the beam is coming off the track, which seems dumb. But anyway, that's their question. They're trying to ask how far up would the bow be? And I'm like, well, I'm going to use an approximation. I think personally you just kind of cut it here. You go like this, and you do halvesies. So you know this is 5280 divided by 2. $52.80 divided by 2. So you know the bottom one is 2640. So this must be 2640.5. And this is the mystery height. It is off the track. So I would go side squared plus h squared, 2640.5 squared. Whoa, 6,996,000. So 6,996,600 plus h squared equals 2640.5 squared minus the 696,9600. So h squared equals 2,640.25. Seems like I messed up here. Maybe not. Let me get my answer, and then let's see how unrealistic it is. Square root. $51.38. That's not good. That's not even close. But sure enough, although unrealistic, I worked the problem, and I'm looking at the answer, and didn't even look at their stuff, and I worked it exactly the same way they did. It says, according to approximation, the center of a rail would rise more than 50 feet off the ground because the triangle will stick up higher than the curve at the base and the length. Actual height is less than the approximate height. An exact solution shows that the top of the curve rail would be 48 feet off the ground. My, that is impressive stuff. So that's crazy. Now, do you think it actually would raise? I don't think so. Personally, I think it gets a little curvy. And I think that 1 foot in real life is picked up in the curvy track if it actually does expand 1 whole foot. Maybe they're making it exaggeration or something, but pretty crazy. That number's big. I didn't trust it, but it turned out I worked it just like they worked it. Wow. Just kind of a stupid problem in a way, I think, but definitely worked a simple problem, used Pythagorean theorem again, worked it just like the book said, and then an old man, was kind of surprised with the result, didn't even trust my answer. Very unusual. Hint 7. Look for patterns. Patterns are like equations. If you see patterns, then maybe you can repeat the pattern and you figure out the pattern, and before you know it, you can figure out, the answer to a really difficult question if you just picked up the pattern. Oh boy, this problem. I don't know if I really want to work this problem. It's the China's population policy, and you look for a pattern in it, and I don't know if it's going to help us any or not. So let me think of cool things with patterns, like 2, 3, 5, 8, 13, 21, 34. Does anybody know what I'm doing? 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 13 plus 8 is 21. That is a cool pattern. It's actually got a name. It's called a Fibonacci. If I go 2, 5, 8, 11, 14, add 3, add 3, add 3, add 3, that type of number system has going up by threes is called arithmetic or arithmetic, or it's got a whole bunch of real cool names. If I go 4, 2, 1, 1/2, 1/4, dot dot dot, I multiply by 1/2, I multiply by 1/2, I multiply by 1/2, I multiply by 1/2, said to be geometric. There are cool things with patterns. So a lot of times, even like when you're playing video games, you're always looking for patterns, because you use that to help you get to the level that you need to get to. Now, the problem that they work by working it, I don't know if it's going to make you any smarter or not, but they could have came up with a lot better book example than look for patterns. I'm hoping when I work the problems, which I'm going to be, grabbing tonight, and I'm going to read through them, and hopefully I can find a good problem for you. Finally, hit 8. Maybe the biggest difference between you and me. Do not spin your wheels. what I do is I'm like, I can only work the problem for so long. Sometimes I get obsessed, yes, and I'm pretty confident because I got good math skill. But you got to understand that, yeah, this class may be hard for you, but every math class I ever took was hard for me. I've taken, let me see, undergrad, I had 40 credits of math. So that's like 3 or 4 credits a class. So like 12 math classes. And then my master's, I had another 12 math classes. And then my doctorate work, I had at least another 20 some classes. Every class was hard. And my problems weren't like a little 1-page solution. I'd have problems with like 30-page solutions. And sometimes I'd get those wrong. I know not to spin my wheels. Now, I try my strategy, I try my strategy, I try my strategy. The idea is get some strategies, get some techniques. Get some methods for solving problems. Now, I'm not going to pretend that I'm like going to solve all your issues with this one little section. By the way, it used to be like 4, but now it's 1. You just got to know when to lay off, and you know. And then some of you are already good. You're already asking for help, and I get that. Here's my thoughts. I'm going to pick 10 problems from 2C. And let's say 50%, when you're all done, and if you got a 50, I turn around and make it a 70%. If you get a 60%, I turn around and make it an 80%. If you got a 70%, I just turn around. Anything over 70%, I turn into 100% on section 2C only. Because I think we could run into a world of hurt. Could be wrong, but since the book switched from like a whole chapter to one section, I'm thinking we can run into some real doozies here. So I'm going to play it safe and like have this little curve set. And then there's going to be the people, oh, what if I get a 55? Well, okay, 75%. And then they'll go, what if I get a 51? And I'll try to make like a 71 or something like that. So I'll try to, throw even subscales in there. But if you get a 65, I'll give you 90%. But as soon as you get a 70%, I'll give you 100% on section 2C. This way I also know if you're actually listening to the lectures. So good luck. I'm going to pick some problems. And I had them picked before, but now after I lectured over the section and worked their problems, probably rethink my selection. That's it. See you later. Let's end this thing.